common usage of the vector space R squared is to represent two-dimensional space, the plane in other words. And the way we usually do that is by choosing an origin, a special point in R squared, and a system of coordinates, which means an x-axis and a y-axis, typically at right angles to each other, like this. And then the way we represent points in the plane by elements of R squared is that a vector AB corresponds to the point which you reach by going A units in the x direction and B units in the y direction. And the reason that this is a useful construction is that every point can be uniquely represented in this way. In other words, every v in R squared can be written uniquely, so in only one way, as a multiple of 1, 0 plus a multiple of 0, 1, like this. Now, other coordinate systems are possible if you choose, in fact, any two vectors which don't lie on the same line. So let's try and draw some here. Here's one F, and here is another G, not necessarily at right angles to each other. Then it's still possible, so long as F and G are linearly independent, we still have this property that every element of R squared can be written uniquely as a multiple of F plus a multiple of G. So this is another choice of coordinatization for the plane, a different coordinate system. Many different coordinate systems are possible. So this idea, a collection of vectors such that every element of the vector space can be represented uniquely as a linear combination of those vectors, generalizes to arbitrary vector spaces through the concept of a basis, which we're going to look at in this video. Here's the definition of a basis then. A sequence of elements in a vector space V is called a basis for V if and only if it has the following two properties. So number one, it's linearly independent. Number two, it's a spanning set of V. And again, before I explore this definition anymore, let me just emphasize that this is a property of a sequence of vectors, right? Not a set of vectors, a sequence of vectors. The order matters. We've already met at least two examples of bases, and I'm going to describe them for you now. So first of all, the vectors E1, which I'm going to call 1, 0, and E2, 0, 1, are a basis of the vector space R squared. You have already seen that those two things are a spanning set for R squared in the last video, and that they are linearly independent. I will actually prove this on the next slide in slightly more generality. So there's an example of a basis of R squared. But as I said on the introductory slide, there are lots of different bases, infinitely many different bases of R squared, for example. So for example, we might take, let's say, F1 will be 1, 1, and F2 to be 1 minus 1. Those two vectors are another basis of R squared. Once more, we showed in the previous lecture that this is a spanning set for R squared, and I think we showed in the lecture before that that those two vectors are linearly independent. Therefore, they're a basis of R squared. Vector spaces consisting of column vectors have what is called a standard basis. And on this slide, we're going to define that standard basis and prove that it really is a basis. So as a reminder, I've copied the definition of basis at the bottom of the screen there. So if you take any field f, then you can define EI to be the height n column vector in f to the n, which has a 1 in position I and zeros everywhere else. So for example, if you were working with height 3 column vectors, so in f cubed, then there would be 3 of these vectors, E1 and E2 and E3, and this is what they would look like. So the set of vectors E1 up to En is called the standard basis of f to the n. So of course that name is implying that this really is a basis, that this sequence of vectors fits the definition of basis. So what I'm going to do next on this slide is to prove that E1 up to En really is a basis of f to the n. So let's do a proof that E1 up to En is a basis of f to the n. This is a two-part definition, so we have to check two things. We have to check that E1 up to En is linearly independent, and then that it is a spanning set. So let's prove that it's linearly independent. To prove something is linearly independent, what we have to do is to show that the only linear combination of E1 up to En which is equal to the 0 vector is the linear combination in which all the scalars were 0. So we will start by supposing that we have elements of the field L1 up to Ln such that L1 times E1, I'm going to underline these so we remember that they're vectors, plus L2 times E2 up to Ln times En is equal to the 0 vector. So the 0 vector in f to the n is just the column vector, all of whose entries are 0. Well, when you add these column vectors up, you can actually see really easily what you get. I mean, imagine, for example, in this example of f cubed, which I wrote over here, well then AE1 plus BE2 plus CE3 will be equal to the vector A, B, C, of course. So here, what we've got on the left-hand side of our equation is just the vector L1, L2, down to Ln, and that is equal to 0, 0, 0, like this. So just looking at the coordinates one by one, L1 equals 0, L2 equals 0, and so on up to Ln equals 0. We've shown that if you had a linear combination of the e's equal to the 0 vector, then actually all the coefficients in that linear combination have to be 0, and that is the definition of linear independence. So now we have to prove that E1 up to En is a spanning set, so we have to take any vector in f to the n and prove that it can be written as a linear combination of the EI's. So let's let V be an element of f to the n, in other words a height n column vector. So we can write V as V1, V2 down to Vn, where the V's are some element of whatever our field f is. Well, then it's actually really easy for me to write V as a linear combination of the EI's, because now V is equal to V1 times E1 plus V2 times E2 up to Vn times En. That means we've written an arbitrary element of f to the n as a linear combination of the e's. So the span of the e's is equal to the whole of our vector space f to the n, which means they're a spanning set. And this is how we do all proofs that something is a basis. We simply check the two parts of the definition of basis, linear independence and spanning. On this slide, we're going to look at a couple more examples of bases in different vector spaces. So we're going to begin with a vector space of polynomials. You will remember that when I write c less than or equal to 3 of x, what that means is all polynomials of degree at most 3 with complex number coefficients in the variable x. So all things of the form a0 plus a1x plus a2x squared plus a3x cubed, where the a's are complex numbers. Then this has as a basis the constant polynomial 1, the polynomial x squared, and the polynomial x cubed. And the reason for that is I think it's pretty clear that every polynomial in c less than or equal to 3 of x can be written as a linear combination of those four things. It's a spanning set because every element, let's say f in c less than or equal to 3 of x equals a0 times 1 plus a1 times x plus a2 times x squared plus a3 times x cubed for some a0 up to a3 in the complex numbers. That's what it means to be a polynomial of degree at most 3 in the single variable x, and that shows us that every such polynomial is a linear combination of 1x, x squared and x cubed. On the other hand, if a0 plus a1x plus a2 x squared plus a3x cubed is a linear dependence relation, if this equals to 0, then we can compare coefficients in polynomials, so it would follow immediately that all of the coefficients were 0. a0, a1, a2, a3 equals 0. So that means the only linear combination of 1x, x squared and x cubed equal to the 0 vector in our space is the linear combination where all the coefficients were 0, and therefore these four things are linearly independent. Let's have an example in a different vector space now. So we're going to look at M2 by 2 of R. That's the vector space consisting of all 2 by 2 matrices with real numbers as entries. As a basis, which I'm going to write like this. E11 will be 1, 0, 0, 1. E12 will be 0, 1, 0, 0. E21 will be 0, 0, 1, 0. And E22 will be 0, 0, 0, 1. Really, this is just like the standard bases for spaces of column vectors, except for matrices instead of column vectors. And again, it's very easy to prove that it's a basis. Let's do spanning first. So it is a spanning set because if you have any 2 by 2 matrix with real entries, so if A, B, C, D is in our vector space, then we can write it as a linear combination of these Eij's just by saying that it's equal to A times E11 plus B times E12 plus C times E21 plus D times E22. That shows every element of our vector space is equal to a linear combination of E11, E12, E21 and E22, and therefore those four matrices form a spanning set. we now have to show that it is linearly independent. And to do that, we'll take a linear combination of the e's equal to the 0 element in our vector space and show that actually all the coefficients had to be 0 in that linear combination. So if a times e11 plus b times e12 plus c times e21 plus d times e22 is equal to the 0 element in our vector space, which is the 2 by 2 0 matrix, then just simplifying what you have on the left-hand side, a, b, c, d is equal to 0, 0, 0, 0. Okay? So a equals 0, b equals 0, c equals 0, and d equals 0. That proves that the only linear combination of e11, e12, e21, and e22 equal to the 0 vector is a linear combination in which all the coefficients were 0. Therefore, e11, e12, e21, e22 is linearly independent. We've shown that it's a spanning set, and we've shown that it's linearly independent, so it is a basis for the set of 2 by 2 matrices with real number entries.